Hi everyone and welcome to the channel. Today we have a special guest that will be coming on shortly. These videos are in sequence, so we're continuing from where we left off. My guest will explain how everything is connected and today's topic, which is how we got arithmetic from geometry. So, hi John.
Hi, Maki.
Would you like to take it from here?
Sure. Okay, so as you can see, the last video that was produced was called Requirement 5 of Euclid's Elements. And so what Maki has done so far is he has explained all the requirements and everything that is needed so that we can proceed to use geometric objects such as points, lines, circles, etc. And what we have now is the ability to realize how we can do arithmetic with ratios. So the first type of arithmetic I want to show you is the arithmetic that we have when we try to, for example, find the difference between ratios, okay, or the sum of ratios. So we have two ratios here, which are displayed by this red and blue line and this light blue line and green line. And we can actually use the fact that similar triangles produce ratios that are in proportion if the correct sides correspond to the sides of each similar triangle. Okay, so for example, we could represent this first ratio with a red line as follows on the y-axis and the blue line on the x-axis, and I've made it dotted because I want to overlay the other lines. Now, remember, you don't actually have to have perpendicular lines like this. It could be any type of similar triangle. Any type of similar triangle will do. So I'm only using this because it's easier to see. So let's represent also the second ratio. And so what I've done here is I've put this light blue line also dotted so that you can see where it is, and the green line. Okay, so now we have two ratios and we want to see what is their difference and their sum. Now, the first thing you'll notice is that they are not referenced by the same magnitude. For example, you can't simply take this red line and join it to this light blue line and say that is the sum. Or you cannot take this blue line or put it like that and say that this little portion here where I'm pointing with the hand is the difference. Can't do that. And why can't you do that? Because they're described by different consequents, okay? So the red line is described by this consequent, the dark blue line, and the light blue line is described by the green consequent. So the first thing we have to do is to find equivalent ratios, right? And we do this with similar triangles. So in other words, what we need to do is find a common magnitude, and it can be anywhere along the x-axis. Okay, so I just chose this point here to give you an illustration. So the measure of these two ratios, or the sum in this case, will just be the concatenation of these two lines, as you see in this first line, described by this magnitude, this common magnitude with three lines over it. Does that make sense? And it doesn't matter where we move these points. The result will always be the same. In other words, 1.41666, or if you look at it this way, again, it will be the same value, and it doesn't matter where you move them, it'll always be the same value, okay? So let's choose a simpler example so that we can see the measures easier. So let's just make the consequence both the same, in which case here we'll have a half plus a half, which is 1, right? Because how do we know this is a half? Because this line is a half of this line and this line is a half of this line. And if we said this, it would still be 1, wouldn't it? And I'm just showing you the measure here. But if we try to see the actual measure of these segments, or what the magnitudes, what names are given to the magnitudes, then we can see that in algebra it will be 2 over 2, right? And of course, these two lines here are joined to give us the antecedent, which is 2, and they are described by the unit consequent, which is also 2. Now remember, it doesn't matter how we do this. We could, for example, have any other ratio which is equivalent. So let's take this one here. So these are still half, aren't they? Yes, they are, right? And here the result remains the same. So what you're seeing is a way to add ratios in geometry, okay? So we're not actually using numbers. We're just using lines. So if we make these units, or the same consequent as a unit, now this is the same as saying this line plus this line, right? Which is the sum of these two dotted lines given by this antecedent to this consequent, okay? And it doesn't, and of course, if we change the magnitude to this here, then it would be exactly taking this line here, placing it, and I don't want to move it all along, but taking this line here, placing it on this dotted line. So this part here would be red, and this part here would go onto the second part of the line. So it's just really the concatenation of these two lines, or the joining of these two lines. Does that make sense? And of course, the sum is also easy. I mean, the difference is also easy because it would simply mean finding the difference between these two lines using a compass and straight edge, right? Do you have any questions so far, Mackie?
No questions. Maybe
Okay.
we can do an overview afterwards, a summation to make everything stick.
All right. So we've dealt with adding ratios, and now let's go to quotient of ratios. Now, quotient of ratios, once again, we represent them in the same way, right? And we have to find a common consequent. And we do this, doesn't matter where we place the points, it's fine wherever we place them. And then we have the quotient of these two ratios, because they have a common magnitude, it's just simply the ratio of this long line to this line. The ratio of this long line to this line, right? That's all it is.
Mm-hmm.
So what you're saying here, let's say we have this, just to make things simple. Okay, so we have that. Okay, now the quotient of these two ratios is simply this long line here, which is this first one, to the second line, which is the second one. And we could make it easier to see by just moving these closer, right? In fact, let's move them over there. All right, so we can see that the ratio of these, the quotient of these two ratios is the ratio of this long line to the short line. We don't care about the consequent anymore because they are expressed already in terms of the same consequent, which is this line down here, okay? So in reality, what we would have done is we would have written something like this. We would have written 4, 1, like that, 4, 1, and the ratio of that to 2, 1, right? Like that. Okay, and because the consequents are both 1, we just simply left with a ratio 4, 2, or any proportional ratio. And of course, 8 over 4 is proportional to 4, 2, isn't it?
Mm-hmm.
Okay, or any other ratio. So we can move it over here, and now we've got 16 over 8, and this is also proportional to 16 over 8, okay? So I'm not going to worry anymore about this. Let's move along to multiplication. So multiplication is done also through division. In other words, it's a reciprocal measure of division. So there are two ways to do this. we could, and let's just use multiplication. Let's say that that's going to be 2 multiplied by 3, just to keep matters simple. 2 multiplied by 3. There are 2 ways to do this. First, we can invert the second ratio. As you see, I've done down here, I've inverted the second ratio. Or the second method means we could invert the first ratio. But let's do them one by one. So to find a common consequent, and I've already done that, I've got the points there, like that. So we found a common consequent, which is this bottom line here. And what we do now is we take the ratio of the long line to the small line, and that gives us the multiplication of these 2 ratios, doesn't it?
Mm-hmm.
So 2 multiplied, this is 2 multiplied by 3. That should be 6. So I've obviously not done something right here. I am in product ratios. Shouldn't be. No, that is right. It is right, because if you take the measure, it is right. Because if you take the measure, it is 6. For example, 8 over 1 1/3 is 6. Okay, so it's right. Now, the measure of this ratio also is 6, okay, as you see over there. But you can place this anywhere along the x-axis. And, of course, the measure always is 6. And where did I have it before? I had it over here, right? So, or over here, I think I had it. Let's just see. Yes. So that's correct. I just didn't show you the measure. So the antecedent here, it's not really 8. It's this line here, this dotted line, this long line which you see on the side here, measured by this consequent. Okay, so we don't really care about the numbers right now. We're only dealing with the geometry. So the multiplication can be done using method 1, where we invert the second ratio, meaning that we measure the first ratio with the reciprocal of the second, right? Or we could do it using the second method by measuring the second ratio with the reciprocal of the first. In other words, flipping the red and dark blue magnitudes. And to find that, we simply do this. And we have the result of the multiplication, which is this long line here in ratio to this line. And if we take the measure, it will be 6, right? Which is, again, the correct answer. Do you have any questions on that so far?
No, I'm good.
Okay. And that's pretty much all as far as the measures are concerned. Now, to understand all these things properly, I would recommend that you download this 20-page article. It's not very long, which explains everything I've just talked to you about. And it goes into big detail, showing you how you move from the geometry to the algebra. Okay, so for example, if we wanted to do division, we're actually taking the quotient of a half and a third, as you see over here, and we can do this little operation here with a half plus a half plus a half over a third plus a third plus a third, because of book 5 and proposition 12. So this evaluates to three halves, right? And of course, if we have to divide a third by a half, we would have 2/3. Now, multiplication is just a reciprocal measure of division. So again, if we were going to do this example here, where we say a half divided by 3. Now, by the way, we're trying to find the multiplication of 2 and 3. So if we say a half divided by 3 over 1, it's going to give us 1 over 6, right? Mm-hmm. Here I'm not using the multiplication of 2 over 3, which I showed you in the applet. I'm using the multiplication of half and a third, right? So in other words, I'm multiplying a half by a third here. But of course, I'm not going to go into detail here. You can read this article and it will give you a lot of understanding. So it does require time and effort and study, but it's really worth it, because what it shows you is how all these things are transferred to algebra through the abstract unit, by the way, whose measure doesn't matter anymore. So if I go back here again to to the first one, in algebra, we don't really care about dealing with the geometry every time. So, and we don't talk about finding a common magnitude, but rather a common denominator. And we call these by the names of numerator and denominator, right? And of course, we refer to them measures. And how do we refer to them measures? Well, we transfer all the properties of geometry. We say that that's 1, that ratio is called 1, that ratio is called 2, 3, 4, etc., right? So we no longer talk about this as a ratio, but rather as the value 4 over 1, or just 4, right? Or just 4. And
Yes.
the same with the second ratio, plus 4. 4 plus 4 is 8, right?
Yes, because now we've given basically names to
Yes,
these
we've given
measures
names.
of the magnitudes.
Correct. And we don't care about the size of the unit anymore.
Mm-hmm.
Because as you can see here, we're assuming the unit is 1 and its size is irrelevant.
Right.
Okay, and then we move on to the definition of fractions in algebra. So what is a fraction in algebra? It's really just a number, which of course is p over 1 and q over 1, right?
Mm-hmm.
Just a number where it's just a ratio of numbers where the numerator is a multiple of the unit and the denominator is a multiple of the unit. And that's pretty much it. So that follows neatly on the completion of the requirements. And if you have any questions right now, I'll answer them.
Great. Thank you very much. First, I have an overall comment.
Right.
This, and then we'll go to questions, and maybe we can sum up everything, like go over addition and the rest of the operations again, just to really cement it. So first of all, the comment, what's apparent to me, like studying modern mathematics the analytical way, and they do things through axioms and the piano axioms, and using recursion and having addition and defining everything through addition of units and what have you. So this just shows to me, because we've talked about Platonism so much and how fundamental it is, it's the underpinning of everything. This just basically, what we're saying is that arithmetic works because of geometry, and that's apparent from using similar triangles and these properties, right?
Yes.
Right.
That's correct, because you wouldn't even know how to do, I mean, for example, why would you say p plus q, p over q plus r over s is equal to p s plus qr over the common denominator, which is qs, right? How would you know how to say that? You don't just, somebody didn't just sit down one day and imagine that that's the definition. It comes from the geometry.
It comes from the geometry. The fact that we're finding a common quotient geometrically is when we connect those 2 points, and we're going to go over that. A common magnitude that measures both ratio. Okay, do you want to just go to the first one and
adding ratios?
Yeah.
Okay, this is the first one. I've just got all this garbage on top of the screen now, so maybe I'll just quickly wipe it out. There's no quick way of doing this except this way, so
that's fine.
In a second I'll just get this out of the way, and you can ask me whatever you want to ask now. Okay, so what do you want to know now on this one?
So basically what we're doing, just an overall, because this is a cognitive shift for lots of people, although it's so fundamental and they used it in antiquity and it makes much more sense. A lot of people might have some trouble even thinking of things as in simple ways as line segments and magnitudes and what have you. So what we're doing basically is we have to we start off, the most fundamental way to start with something is to consider magnitude, right?
Yes.
So
yes.
we set a line segment, and that's a magnitude. That okay? And in order to talk about that magnitude, we always need some sort of other magnitude as a reference, because otherwise it's meaningless, right?
Yes.
And that is a ratio.
Yes, and the comparison of the two is a ratio.
The comparison of two magnitudes is a ratio.
Yes.
So we have two magnitudes, the comparison of the two is a ratio, and then the next logical question is, now that we have a ratio, how do we do operations with other ratios to further build complexity and to gain knowledge? So how do we add ratios, how do we subtract, and how do we do the rest of the operations? Right?
Right.
So then in turn we can take those magnitudes and use them as sides of a triangle.
Yes.
And then from the properties of triangles is that the triangles that are created from doing that, all possible combinations of all those triangles, what
yes.
you're doing now, as we're scaling these triangles,
yeah,
they're all in proportion. So all the sides, all those ratios that are created from the scaling of the sides are always in proportion.
Mm-hmm.
So we use the magnitudes from the first ratio. Then we do the same thing for the second ratio, and then finding. So afterwards, if we want to do operations between these two ratios, we can't just, as you said in the beginning, just put one on top of the other arbitrarily, unless they have a common measure. And
yes.
that's what we're doing with a consequence. So,
yes.
and the geometric underpinning of finding the consequent is when we pull that green and that magenta point so as to coincide.
Yes.
Okay.
Yes.
Okay.
And we can put them anywhere along the x-axis.
Yes.
Okay. So if we put them over here, then it gives you the answer you're used to, because the length of this, as you can see, is 2 and the length of that is 3 in terms of numbers. So if we show numbers, now you can see them as they are in algebra, right?
Mm-hmm.
Okay.
Great. So we went from geometry in the previous video, so now we're gradually going into arithmetic. So what would be the next logical step in our process of building this framework?
Well, the next logical step is to complete the transition to algebra through the abstract unit. In other words, to give these line segments, these ratios and line segments names, so that we don't need to sit and draw triangles anymore, and we can just discuss them in algebra without referring to the geometry. And that's very easy to do, because we can actually do that right now. In this video, we can say, let's call a ratio of equal magnitudes the unit, and then from that unit we derive other numbers. Okay, so this ratio is in effect the same as saying this. Sorry, that's too long. It should have just been one block long. It's the same as saying this number now is the number 2, because it's the ratio of this ratio to this ratio. This is the unit ratio, which should really just be the same as this. So we call this 2. And because we know it's the unit ratio and we don't care about the size, you know, we just simply write it down as 2 instead of 2 over 1, okay? Same here, 1 over 1 is just written as 1. That's it. And 3 and so forth. And then, of course, the fractions end up being numbers. So, for example, if you really wanted to write the number 2, this number 2 in the long way in algebra, you would write it as 2 over 1 over 1 over 1, right?
Yeah.
This is a fraction.
Yes.
But because we know the denominators are the same, it's just 2 over 1, right?
Yes.
Meaning it's 2. And so you basically completed everything now from geometry to algebra, including the operations. And so now we don't have to, in algebra, we don't have to join lines. So for example, we don't have to join these 2 lines anymore. We can just say 2 plus 1 is equal to 3. And that means the concatenation in geometry of these 2 lines or any proportional lines to these 2 lines. So for example, it can also mean this in geometry. It can also mean that. But it still evaluates to this, which you see in front of you here in algebra. Okay? Still evaluates to 2 plus 1 equals to 3.
So is this the way the ancient Greeks saw arithmetic?
This is precisely what the ancient Greeks were thinking of, especially when Euclid wrote down Book 5 of his Elements. The purpose of Book 5 and Book 6, in fact, was to explain all this theory. Now, unfortunately, Euclid hasn't done it as well as I've shown it to you. In fact, he's left out most of the obvious details, which are the ones that I'm showing to you. He's focused more on the theory of proportion and the theory of ratios rather than on the arithmetic using sum. But he didn't leave us without help, because Proposition 12 tells us how to do all these things, doesn't it? Proposition 12 says that if we have, let's do this. Proposition 12 says that if we have 2 over 3, we can say that that's equal to 2 plus 2 over 3 plus 3, right? Yeah, and so on. We can add any proportional ratio. We could add 4 here and 6 here, right?
Yes.
That's what, and this, what you're doing here, this process here, in effect, is the similar triangle story.
Exactly.
It's the same thing. There's no difference. And so geometrically, all you're doing is working with similar triangles in order to find the resultant ratio of either difference, sum, quotient, and product. And that's pretty much it.
Great. Would you like to add anything else before we close this up?
No, thanks for having me, and I hope your viewers will have learned a lot from this. And also, just to summarize, this document is very important, and you might want to place a link to it.
Yes, I
in
will.
the details section, and have them study this document, because it has everything you need to know. And that's pretty much it.
Great. Well, I'll try to make a few videos, as I did on Euclid's Elements, on this material, just going through it, struggling with it, and just maybe make a few mind maps about it, so it just sticks. Because these things are sort of, they're simplex, but they're not simple, or I don't know. It's there's a lot of depth to it.
Well, I explained all of this to a Greek professor who has degrees in mathematics, physics, chemistry, and applied mathematics, and it took him 35 minutes to understand. And once he understood, he was completely blown away, and he called me a great thinker. So there you have it. I mean, it's wonderful knowledge, and it would have been nice if Euclid had done this, so that everybody who had studied the elements would actually know why they do the things they do.
Yes, of course. Great. Well, thank you very much, John, for the presentation. And yes, that's it. Well, let's wrap it up then. And we'll be again here soon, going further and further into mathematics. Okay, thank you. Bye.